So here in this class we will discuss the next type of digital pulse modulation, that is adaptive delta modulation. Okay, you know that delta modulation is a kind of digital pulse modulation where each transmitted pulse is represented by its 1-bit equivalent. Okay, and one of the major drawbacks faced by delta modulation is it introduces two errors, that is the slope overload error and granular error, or the slope overload distortion and granular noise. Okay, so we have already studied in the previous class. So here I will explain what is slope overload and granular noise once again. You know that in this delta modulation system, the step size delta remains constant. Okay, so this represent the input message, the input sinusoidal variation, or the input message x of t. So we are considering a delta modulation system where the step size delta is a constant and is independent of the input amplitude x of t. Okay, now we can see that during this portion, when the signal amplitude is changing at a very faster rate, the stair-step approximated waveform is not able to follow the rapid variations of x of t. Okay, so the error introduced due to this kind of distortion is called as slope overload distortion. And during this portion of this input waveform, we can see that the message is remaining a constant. The input is not varying continuously, but rather the input amplitude level is almost a constant. In that case also, the stair-step approximated waveform is having two levels, a plus delta level and a minus delta level, or the stair-step approximated waveform is fluctuating between two amplitude levels. And the error due to this kind of phenomenon is called as granular noise. Okay, a solution for this kind of errors in delta modulation is to design a practical modulator where the modulator itself is able to change the step size with respect to the input signal amplitude. That means if the signal amplitude is increasing at a very faster rate, the delta, the step size, should increase so as to follow the input variations. And if the input amplitude is changing at a slower rate, the step size should decrease. Okay, or in simple words, if the amplitude is increasing, if the amplitude is increasing at a faster rate, or if it is changing at a faster rate, the step size should increase. And if it is not changing, if the input amplitude is not changing at a faster rate, the step size should decrease. So such a practical modulation system is called as adaptive delta modulation. Okay, so this modulation is the refined form of delta modulation and is a kind of modulation system that solves granular noise and slope overload error, and is very similar to delta modulation except that the step size is a variable function according to the input signal amplitude. We will discuss the transmitter part. If you compare the transmitter part of an adaptive delta modulation with that of a delta modulation, the only difference is that we have a logic for step size control. So this is an additional block included in the transmitter part. So we can see here. So the rest of the blocks are very similar to that of a delta modulation system. Okay. Here in this case, the step size of the signal will increase or decrease depending upon the output of this 1-bit quantizer. So the 1-bit quantizer output is connected to the logics for step size control. So if the 1-bit quantizer output is high, the step size will increase, and if this 1-bit quantizer output is low, the step size will decrease. Okay, so this is how the variation or the change in step size is introduced. The name adaptive because it is adaptive to the step size is adaptive to the input signal amplitude. Okay, so here at the output we are obtaining again a 1-bit approximation of the input message signal, but you know that the step size is varying depending upon the input signal amplitude. Okay, so this figure shows the adaptive delta modulated waveform. So during when the signal amplitude is increasing or changing at a very faster rate, we can see that the step size is increasing. Okay, so during this portion, the step size is increasing so as to follow the input signal variations. Okay, here x of t represent the input signal and x q bar of t is nothing but the stair-step waveform. Okay, and it can be clearly seen that the step size is a variable function. Okay, so during this portion of the signal, when the signal amplitude is changing at a lower rate, you can see here the step size is also decreasing. Okay, so in this way we can say the both slope overload error and granular noise is eliminated. Okay, now we can see what is there in a adaptive delta modulation receiver. This adaptive delta modulation receiver contains two portions. This is the first portion and this is the second portion. We call it as the accumulator. Okay, the first part, that is the logic for step size control, produces the step size from each incoming bit. Okay, so here we have a stream of binary ones and zeros. So this is applied to the logic for step size control and a multiplier. So at the output of this multiplier we have the step size. Okay, and the previous input and the present input decides the step size. Okay, so this step size is then applied to an accumulator which builds up a staircase waveform. So at the input of this low pass filter we have a step zeros is converted into its corresponding stair-step waveform. Now the function of this low pass filter is to smoothen the staircase waveform and to reconstruct the original message. Okay, so here at the output of the low pass filter we obtain the original message as it is transmitted. So let us see what are the advantages of adaptive delta modulation. So as we discussed, it eliminates both slope overload and granular noise. And there is one more advantage for the system. This modulation utilizes bandwidth in a more efficient and effective manner. Okay, so better bandwidth utilization.